There are still a couple of seats up here close to the front in the first 3 rows on this side. There's one over here. Ladies and gentlemen, it's my pleasure to welcome you to our continuing GTL program. And our speaker this morning needs no introduction, but nevertheless, it's appropriate that I mention that he has been awarded and designated as the Burwell Lecturer, and this will be his Burwell Lecture this morning. Can you hear me all right in the back there? Okay. Now, I also wanted to mention that Enrique has, since getting his PhD at Stanford, under the direction of Michel Boudard, done extraordinary work in the GTL area and has touched Fischer-Tropsch and hydrogen production just about every area. And so we're just delighted to have him on our program. And I won't hold up his lecture anymore.
Thank you, Cal. Can you hear me from the back okay? All right, so I think your microphone may be overwhelming in this small room. I'm going to tell you a little bit about an area that we sort of went in with great trepidation about 3 years ago or so. We had never worked in the area. It has to do with high temperature reactions of methane on supported metal clusters. We did that, but before I do that, I want to recognize the fact that I'm here today sort of in memory of Bob Burwell, after whom this award, this lectureship was named. One of the greatest scholars in catalysis that we have known, and again, someone that was no longer with us. He died very close to the last meeting, so I'm sorry he cannot be here, but again, it's a pleasure and an honor to be here to honor his memory at this meeting. We entered the area with a very naive idea of what we should do, and what we should do is we should keep it as simple as possible. We said if you're reacting methane on a metal cluster, why don't you assume that methane does what it tends to do in metal clusters, which is to fall apart. When it falls apart, it gives you hydrogen and it gives you carbon. And if you kinetically couple that reaction with a co-reactant that is able to remove the carbon by providing a reactive form of oxygen, you can close the catalytic cycle and effectively generate synthesis gas, whether that co-reactant is CO2, water, or oxygen, in the case of partial oxidation or combustion, or you can even do the reaction in the Okay, now turn down the hearing aids. You can also do this.
You're getting feedback from that. Sorry.
Limited space.
Okay, so don't let me move that. You can also do the reaction by, this is not going to work.
Okay.
It's fine.
Okay, how's that? You can also do the reaction in the absence of a co-reactant and effectively run the danger of forming carbon. What I'd like to do today is I would like to take you in a bit of a tour as I take you through the kinds of mechanisms, as many as it may take in order to explain the chemistry, that we have been able to unravel, the evidence that we have been able to obtain by going away from simple rate expression measurements and beginning to interrogate elementary steps. Look at the effect of cluster size, the effect of support, and the effect of the identity of the metal on both the mechanism and the reactivity of these materials. Try to make a connection to explain something that we had never really intended to explain, which is what happens to this carbon whenever you have nothing to take it away and you begin to form carbon filaments. And finally, the newest area, given that we seem to have made more progress than I ever expected in those first 4, is to actually move it into what appears to be an order of magnitude more difficult, and that is what happens when the oxidant is O2 rather than CO2 or water. The first thing that we tried to do was we tried to eliminate artifacts, and you have two problems that immediately face you in this reaction. One of them is that you have to do this in a reactor, at least if you want to do catalysis, and that introduces all possibilities of gradients that lead to local temperatures and concentrations that have nothing to do with what you measure in the fluid phase. And the other one is that this reaction here is not a very favorable reaction. It's an endothermic reaction, therefore prone to temperature gradients, but also limited by equilibrium. The two things that you need to do is, first of all, to eliminate the artifacts, and you do that by diluting and diluting some more until effectively further dilution does not lead any changes in the measure rate. And that's what I showed you here, where we have diluted at both the bed and the pellet scale, and we have changed the size of the pellet, and we get the same turnover rate. And then finally, you're faced with the fact that you want to measure a forward rate of a reaction when there is a contribution from the reverse rate. And what you need to do in that case is you need to account for how far the reaction is from equilibrium by using this simple expression and extract from your measure rate effectively the rate of that forward reaction. If you take those two things into account and you do it rigorously, you actually get a much simpler picture than we did before we were able to do that. We begin to look at a rhodium system. It's a simpler system that does not tend to deactivate. And we look at the effect of various reactants, in this case methane, on the rate of the forward reaction for the CO2 reform. And what you see here is that at a given CO2 pressure, the rate is linearly dependent on the methane concentration. You do the experiment now at a range of CO2 pressures, and what you find is that you not only are still linear, but it is the same straight line. Therefore, what this tells you is that the rate is independent of CO2 pressure, and it is first order in methane. That's as simple as it gets, and because it is so simple, it really does not carry very much mechanistic information at this point. We also find that the reaction rate is not dependent on any of those other molecules, except insofar as those may affect the reverse rate. But we have eliminated that contribution by the approach to equilibrium correction. And finally, you want to ask the question as to whether what we reported here for rhodium is actually applicable beyond. And this is the behavior that we get when we get to a prototypical nickel-based catalyst for the CO2 reforming reaction. Again, a straight line, an independence on the co-reactant concentration, and a linearity on the average methane pressure. So this is CO2 reforming. I wanted to make a connection among the various reactions of methane. So a reasonable question to ask at this point is, what happens if I now go to steam reform? What happens if the co-reactant is now water as opposed to CO2? Do I still get a first order type dependence? Do I still get no dependence on the identity and concentration of the co-reactant? And moreover, is there a difference between CO2 and water in the way that they co-react with methane, in the way that they remove that carbon from the surface? Well, if you look at the rate of the reaction versus methane pressure, and you do it in the presence of water and the presence of CO2, you get the same identical straight line. That means that methane has not recognized the co-reactant as being different in the case of water and CO2. And of course, the first order rate constants are identical for those two. This seemed to indicate that since neither the identity nor the concentration of the co-reactant matters, that you're really limited solely by the rate at which you activate a CH bond on a predominantly clean surface. Since if the surface were not clean, the co-reactant would clean it to different degrees and therefore should affect the rate of the reaction. Well, if you look at the effect of water, there is also no effect of water on the rate of the reaction. And if you now ask yourself the question, if it indeed is methane activation on a clean surface, why don't we look at methane activation on a clean surface? What we can do is we can stoichiometrically react methane on a surface and look at the rate of that reaction. The problem with doing that, of course, is that unless you have a kinetic couple, you're going to build up carbon on the surface and you're not going to be able to go on forever. But you could extrapolate the rate of that stoichiometric reaction to zero carbon on the surface, to the initial stages of that decomposition, and effectively calculate a rate. And when you put that rate on the same basis here, you end up with something that, again, not only does not depend on the identity of the co-reactant, does not depend, at least initially, on whether you have a co-reactant there or not. It appears to be CH bond activation all the way. This is rhodium. The question is, what happens as you go out to other types of materials? Well, the picture so far is one that seems sort of suspiciously simple, and that is that first order in methane, the same rate constant for those three reactions. Effectively, the surface is predominantly clean, and this is the kinetically relevant step for the reaction. The clean surface is something that we can begin to infer from an unfortunate experiment, one that never worked for the intended purpose. You can look at the surface by infrared and you see nothing. So therefore, there's no co-adsorbed species that actually are infrared active. That makes it useless for mechanistic information, but it does tell you that you have no infrared active species. The other one is you can look at kinetic isotope effects and sort of suspect that if methane is involved in the kinetically relevant step, that there should be a normal kinetic isotope effect. We go ahead and carry out the reaction. For the CO2 reforming with CH4, we see CD4, and there is a normal kinetic isotope effect of a value that is reasonable at these fairly high temperatures. We do the same reaction with water. We label the methane in this case, and we get the identical kinetic isotope effect. This did not notice that there was a different co-reactant in the gas phase. And finally, if we choose to label the water instead, we actually get no additional kinetic isotope effect. That means that the isotopic identity of that water molecule is irrelevant for the rate of the reaction. Again, it does not appear to be involved in any kinetically relevant step. Well, what about methane decomposition? We can do the methane decomposition with CH4. We can do the methane decomposition with CD4. We can take the kinetic isotope effect that we observed for that decomposition reaction, and we get a value that is very similar. And again, this is for rhodium. Now, I don't have the time to go and tell you that we haven't found any difference for any of the other metals, and I will do that in a tabular form that perhaps is not the easiest way to do it. All that I want you to do is I want you to compare the three values for each metal for the kinetic isotope effect and the turnover rate. This is the rhodium data that you have seen. This is the platinum data that you have not seen. This is the iridium data. This is the ruthenium data. And this is the nickel data. And again, of course, the turnover rates are going to be different because the reactivities are going to be different. The kinetic isotope effects are quite similar, although there are slight deviations as you go from metal to metal. But again, what I want to point out is that it doesn't matter which co-reactant you have on any of the metals for either the kinetic isotope effect or the turnover rate. So the conclusions do not change as you go from metal to metal, which is indeed fortunate. So if we go one step further and take a bit more of a risk in proposing what is going on, we can begin by saying that methane goes and effectively activates on that surface. It goes to a transition state. It eventually breaks up into pieces. This is going on and off. It eventually breaks up into pieces, and effectively the CO2 will dissociate on that surface. It will give you some oxygen. That oxygen will react with the carbon that you have formed to give you CO. The CO will desorb from the surface. The hydrogen will desorb from the surface, and there will be some water as a result of the accidental recombination of hydrogen and OH groups. And in fact, this is all you need in order to complete a catalytic cycle, whether it is correct or not. That is presumably the kinetically relevant step. The question is, how do you prove the kinetic relevance of that step beyond the isotope effect? Well, one way that you can do that is by looking at the reversibility of that step. We know how reversible the overall reaction is. We can actually look at the reversibility of the CH bond activation step by effectively doing a reaction in which we're able to identify any methane that went to the surface and came back to the gas phase again. We normally do that using isotopes, and we look now at the isotopic scramble as an indication of a reversible CH bond activation. So we can take a mixture of CH4 and CD4 now rather than separate experiments. We can calculate the rate of going back versus the rate of going forward. That is effectively a measure of exchange over reaction. That is the reversibility of CH bond activation. And that gives you a very small value. That means that the step is nearly irreversible. If you compare that to effectively how far the overall reaction is from equilibrium, you're exactly that far away from equilibrium. So of course, the most irreversible step just needs to be just as far from equilibrium as the overall reaction. That's rhodium. When you do it in ruthenium, you get a similarly small number. Again, very similar to the overall approach to equilibrium. And when you do it on platinum, again, the number is slightly larger because it's a more active catalyst, but it is because you're closer to equilibrium. It turns out that I should not have to give you any more evidence that this is the only kinetically relevant step in the overall sequence, except for the fact that even though this is correct, and that is when and only when you have a single step that is kinetically relevant, is that step exactly as far away from equilibrium as the overall sequence. That would require about 2 pages of equations to show you that. It's probably better to show you that the other steps are quasi-equilibrated and get it over with in a more entertaining fashion. So now if we look at this step right here, how reversible is the hydrogen recombination and the water formation in this overall sequence, we're going to take the same approach. What we're going to do is we're going to put an isotopically identifiable version of either D2 or D2O in the system, and effectively look at how it mixes with what comes out of the reactor. So the experiment is very simple. We're going to add a small amount of D2 into that system, and we're effectively going to ask how many times do you come back out and have you mixed with the H, the protium that is there as part of methane. If you do this very, very quickly, you will reach a binomial distribution and you will call yourself quasi-equilibrated. If you don't get any HD, you will call yourself irreversible. When you do the experiment, again on a rhodium-based catalyst, and you measure the distribution of the 3 isotopomers, this is what you get. When you calculate what they should be according to a binomial distribution, that is what you get. Therefore, you have quasi-equilibrated hydrogen adsorption and desorption. But actually, there's something else that you should check, and one of them is how much hydrogen is there in those gas phase isotopomers. It turns out that if you take all of the D2 that you put in the gas phase and all of the H from the hydrogen that you have reacted, and you put them together, you would expect that the hydrogen to deuterium ratio in those isotopomers would be 0.7 for this experiment. And what you find experimentally is indeed that is what you have. But this experiment has additional information because it turns out that there is another product that should be able to now mix with the hydrogen pool that you have on the surface. If water adsorption, desorption is quasi-equilibrated, you would expect now that the amount of deuterium in water will be the same as in hydrogen, and that you will get a binomial distribution, and indeed you get both. Here's the hydrogen content in the water, and it is a binomial isotopomer distribution. So those steps are quasi-equilibrated, both of them. Now, what about this step? This is the CO2 dissociation. Actually, there's been a lot of controversy in the literature, many proposals that CO2 dissociation is actually the kinetically relevant step. What is the experiment that would tell you whether it is or not? Well, again, what you do is you take an identifiable form of CO and you ask it how far do you mix into that pool of molecules that you have in that reaction. So we carry out the reaction with carbon-12 everything. We add a very small amount of carbon-13 CO to the system, and we look at how rapidly those two equilibrate with each other. If you get the same carbon-13 content in both CO and CO2 in the time scale and the residence time required for methane conversion, you effectively have a quasi-equilibrated step. The experiment is carried out with purely labeled CO and unlabeled CO2. We look at the carbon-13 fraction in the products, and it is identical in the two molecules. Therefore, that step is quasi-equilibrated. You can do that for platinum, and again, what you look at is those two being identical to each other, even though they started quite differently at fairly low conversions for this system. And if you do it on iridium, again, the numbers are very similar. So this shows that CO2 dissociation does not enter in any way measuring the reactivity of those clusters in methane activation. Okay, so if you have quasi-equilibrated CO-CO2 interconversion, and you have quasi-equilibrated H2 and H2O adsorption desorption, what reaction do you have? Well, you have water gas shift. So therefore, this will require that if those two steps are quasi-equilibrated, the overall water gas shift reaction would be equilibrated. And the way that you make sure that that is consistent is you effectively calculate how far away water gas shift is from equilibrium. If this is 1, that means it's quasi-equilibrated. If you look at all of the catalysts that we have looked at all of the temperatures that we have looked at, we effectively get something that is very close to 1 with an experimental error. Therefore, for those of you that want to make CO versus CO2, you're in really significant trouble because that is nothing more than a function of the water gas shift equilibrium for that reaction. Okay, so we're getting to the end of the reforming part of the chemistry, but I've left out something. I told you that that was the kinetically relevant step. I measure a rate constant for CH bond activation on what appears to be a reasonably clean surface. And then I need to answer 2 more questions. Now that I know what I'm measuring, and I think I can measure it rigorously, the question is how does that change as I change either the identity of those metal clusters or the size of those metal clusters or the underlying support on which I have placed those metal clusters. Well, this is what I get as a function of metal dispersions. These rates are normalized by the dispersion of these materials as measured by hydrogen or CO chem absorption. This is what I get on a rhodium catalyst for steam reforming. The size is going from about, in this case, 8 nanometers to about 1.5 nanometers. And all of those points encompass a range of supports, all of which may change the dispersion of the rhodium, but do not change the reactivity of the rhodium. We can do the same thing for ruthenium, and we get the same general trends. Of course, a different turnover rate for the reaction. We can do it on iridium, and we can do it on platinum, and we can do it on nickel. And in all cases, we have mixed all the supports, and we have not had to generate a new trend line in order to be able to describe the data. Of course, by now you know what happens if I do CO2 reforming rather than steam reforming, and that is that the trends are the same, and the absolute values for those numbers are also the same. And of course, if I put one on top of the other one, you can't tell them apart. So for every catalyst on every support that we have looked at, the only thing that matters is the extent of dispersion and the identity of the metal, not the identity of the concentration of the core reactant. Okay, so now I want to end this part by effectively talking about selectivity. Nobody ever worried about selectivity, at least I didn't up to this point, because effectively that is given to you by the water-gas shift reaction equilibrium. But there is a selectivity issue, which is what happens if you do not take away the carbon fast enough from that system. Well, what happens is bad things happen. And of course, unless you're in the business of growing nanotubes or filaments, this is not something that you want to have happen during methane reform. What happens is, especially in the case of nickel, but also in the case of some of the noble metals, you begin to generate filaments, the shape, size, and extent of wall thickness depending on the size of the crystallines. Well, presumably we have a mechanism that tells us how we put carbon on the surface, and also presumably what that carbon concentration should depend on as far as the reactant and the product concentration. Can we use it to predict something, or at least to be consistent with something that we never expected to have to take into account in our data? We know that carbon grows predominantly by the formation of the nucleation of a filament and the diffusion of carbon either on the surface or through the bulk of one of those crystallines. This is the diffusion equation. That surface chemical potential or activity is what we have on the surface of a nickel crystal, and we know for our mechanism how it should depend on this ratio of reactants and products. That is what sets the carbon activity on that surface. So if this is what sets the carbon activity and the diffusion rate is proportional to that carbon activity, what do we expect to find? We can go to a microbalance that allows us to do this at reaction conditions and measure the rate of carbon formation. And when we do that, and we take the rate of carbon formation versus this activity surrogate that we have here, what we have is at low values we have no carbon that is formed. As we increase the value of this parameter, we get nucleation and growth and the expected linear dependence predicted by that diffusion equation. And then finally, if you get beyond the nucleation point and past this point, if you have too high a carbon activity, what you actually get is encapsulation. When you encapsulate, you neither grow filaments nor do the methane activation reaction. Everything actually stops. And if you take micrographs at every one of these points, you can confirm that what this dynamic data seems to suggest is actually correct. You can take micrographs at low very carbon activities, and you see no carbon. This is actually the carbon polygrid that we're using to hold the sample. If you get into the nucleation and growth region, you can actually detect that almost every nickel particle, but especially the large particles, have begun to grow carbon. And then finally, when you get to very high values, you actually get encapsulation. You can actually see that there's a carbon layer that has formed, presumably because this particle became a bit schizophrenic and began to grow filaments in every direction. And then obviously the stable way to finish that is to close a capsule around your particle. That was the easy part, even though I had expected to spend quite a bit more time. The fact is that by removing some of the artifacts and by trying to measure true kinetics, the system became a lot simpler. Some of you may tell me, well, the real system is limited by transport. And of course, my answer to you is we'll put the transport when we get there. But if we're trying to get some information about the effects of particle size supports and about the mechanism, we need to remove those layers ahead of time. But then we went too far, and we said, well, given that we have the tools to be able to look at this chemistry, why don't we go now and put O2 into that system? This one gets more complicated. This one does not have a very clean endpoint, and I may not even get to the semi-clean endpoint where I was supposed to get given the time limitations. But the fact is that what we wanted to see is what happens if you use O2 as the source. of that oxygen to remove the carbon. And again, we all know that what we would like to do is what is called partial oxidation. It is a mildly exothermic reaction. It leads to very gradual changes in temperature in a reactor, and it gives you the right stoichiometry. There is, however, a selectivity issue, and that is that downhill, way down there is another place where you could go, and that other place is going to be CO2 and water. This is a combustion reaction. Once it gets going, there's no way to really control it because it is so exothermic, and it now leads to a temperature profile that is much more likely to look like that than it would like that. The question is, which one is going on? And if we find out one versus the other one, what is the mechanism for that reaction? I want to ask some questions that I didn't have to ask before. Since I have oxygen around, can CO ever get out of that surface before it reacts with oxygen? In other words, can I ever put CO in the gas phase instead of CO2? Even if I can, would it ever leave the reactor before it finds another O star, another chemisorb oxygen, and give me CO2? For this chemistry, is CH bond activation also the only kinetically relevant step? And if I have oxygen around, does it affect the rate of CH bond activation? Those are questions that have been answered in the literature, at least with some controversy. So I would like to see if we can take the approach and try to answer. The first thing that we do is we take a reactor. We have diluted the reactor about 20 times more than we ever had in the case of reforming, because this reaction is much more exothermic than the other one was endothermic. If we begin to increase the residence time in a flow reactor, what we find is that, of course, we convert more and more of the oxygen. The rate of CO2 formation is not changed, and we see absolutely no CO in the system. The CO selectivity is 0 as long as I have O2 around. As I begin to deplete the oxygen, what happens is I begin to see CO. The selectivity to CO will increase, but I also see something that I don't want to talk about right now, but I will come back later. There's no reason why the rate should take this jump as I deplete the oxygen, but it does. And of course, that means that the selectivity to CO2 decreases, the CO begins to appear. As oxygen is depleted, I'm either doing partial oxidation for the first time, or I am doing CO2 and steam reforming and making CO. But as long as there's O2 around, there's no CO that ever leaves one of those reactors. Now, it turns out that the most convincing way to tell you that this is not a temperature effect is to do the following. And maybe you won't believe me, or maybe you won't see it from the back. But what I have done is I have changed the residence time two ways. By changing the amount of catalyst and by changing the flow rate of reactant. In one case, there's a lot more heat in that reactor than in the other one, and I get superimposed data points. That means that this behavior is not a result of any local temperature gradients. This spike is not an ignition type process as expected from exothermic reactions. These are true kinetic effects, strange as they may seem. Okay, so the same thing happens with ruthenium. This is not something that is unique to rhodium. Here's ruthenium. As long as I have oxygen around, all that I'm seeing is CO2 and there's no CO. As soon as I deplete the oxygen and get down to 0, I get a sudden increase in the rate of the reaction. The same behavior that we saw in the case of rhodium. So what I conclude is that there's no such thing in this system as partial oxidation, at least most of the way. So I might as well look at methane combustion, because those are the kinetics that seem to matter here. We have done competitive reactions, and we have convinced ourselves that there's no way that CO could ever leave that reactor, because the rate is about 40 to 100 times faster at this condition. So therefore, as long as you have oxygen, CO does not have a shot to get out of that reactor. After all, CO oxidation takes place much closer to room temperature. The kinetics are actually very simple, and now we're going to begin to get in trouble in a while, but for now, let me follow the same approach. Here is the methane partial pressure. The rate depends linearly on methane partial pressure. If I look at two different catalysts on different supports and slightly different dispersions, it is the same behavior. The rate is a little bit different. The rate is independent of O2 concentration. It is 0 order in the co-reactant. The rate is independent of CO2 and water added to the system at these high temperatures. So far, it looks very simple. So I am led to conclude that it is CH bond activation all the way, but now I'm left with the following dilemma. This rate expression would be just as consistent with CH bond activation on a totally clean surface as it would on a totally covered surface. And I don't know which one it is right now. So what I do next is I look at the rate of methane combustion and I compare it to the rate of reforming. Remember, it's the same for both water and CO2. And what I get is a much higher rate of combustion than I do for reforming. This was on a clean surface, so I cannot say that this one is also on a clean surface. I'm left with the alternate possibility, and that is that the CH bond is being activated on an oxygen-covered surface, and that is a faster reaction than what you would get on a clean metal surface. Okay, if I look at kinetic isotope effects, I get a value of 1.85. It is quite similar to what I get in the case of reforming. Again, this is consistent with CH bond activation being the kinetically relevant step. If I do it with ruthenium, a linear behavior on methane, I have a rate constant, which in this case is 0.61. I have a rate constant which is lower, but notice that this difference is only about a factor of 4. It was much larger in the case of rhodium. The fact that the combustion and reforming are closer to each other in reactivity is what leads ruthenium to give you a higher CO concentration when you have methane-oxygen mixtures, because the reforming reaction is able to take place at a comparable rate. If I look at kinetic isotope effects, again, they're almost indistinguishable between what appears to be happening on an oxygen-covered surface and what appears to be happening on a metal-covered surface. So everything suggests now that a CH bond activation put on an oxygen-covered surface. If I look at the effects of CO2, O2 and water, again, this is what you get on ruthenium, just as we did in the case of rhodium. No inhibition by products, no apparently kinetic dependence on oxygen. Two questions quickly. The first one is, do I have an oxygen-covered surface during the reaction? I cannot really tell. I have no way of looking into that reactor and finding anything absorbed at 700 degrees. And even X-ray absorption will become a bit of a nightmare because of the highly exothermic nature of the reaction. But what I can do is I can try to put oxygen on the surface, and then I can do the classical experiment in which I try to take it off and see how strongly oxygen is bound on that surface. When I do that on rhodium, I get a temperature program desorption. This is isothermal, and this is temperature program up to this point. When I do it on ruthenium, I get, again, the temperature program desorption. These are the typical reaction temperatures what we operate. This over here is 800 degrees C, and it looks like the oxygen is really not coming off on its own. That doesn't mean it's there during the reaction, because the methane could be taking it off. But the fact is that by itself, it would not come off. These are the Arrhenius plots for the oxygen desorption rates that we get from this kind of an experiment, and it is an interesting exercise to do the following. Suppose that the reaction is taking place as I show you here, by methane reacting on two oxygens, and that this is the oxygen desorption step. What I'm measuring here is the rate of desorption, is the reversibility of that step. I know how to calculate that from my steady-state catalytic experiments, and I know how to calculate that from my temperature program desorption from that surface. When I take those rate constants for those two reactions, and I take the ratio of the two, the value is extremely small. What does that tell you? It tells you that this step is irreversible during the reaction. Something that I could have shown you just the same by telling you what happens when I use an isotopic mixture of oxygen 16 and oxygen 18, and that is that I get no isotopic scrambling between the two. Okay, now, is an oxygen-covered surface more reactive? That's a little bit more difficult to demonstrate, but one can try to do the following. You can try putting oxygen on that surface, and rather than desorbing it in helium, what you can try is you can try removing it by using methane as the reactant. And when you do that, this is what you get. Okay? You get the evolution of products, you get the evolution of water, CO2, and CO. And what you find is that as you remove the oxygen from the surface, the fraction of the carbon that comes as CO increases. In other words, at full coverage, you're making CO2, as we do during the catalytic reaction, and as you deplete the surface of oxygen, you begin to make CO. That doesn't answer the other question, but this one does. Suppose that I look at the rate at which methane is converted on an oxygen-covered surface. This is what we get whenever we convert methane on an oxygen-covered surface. This is the blue one that I have here. This is how much of it is CO and CO2. This is what I get when I decompose methane on a clean surface. So I have moved the temperature of methane activation by about 150 Kelvin in the process of putting oxygen on that surface. This is not quantitative, but it's at least consistent with the conclusion that the oxygen-covered surface is more reactive for this reaction. Okay, dispersion effects, which I show you for reforming and which were quite sort of consistent. Dispersion effects for the two materials that we have looked at, rhodium and ruthenium. Again, it appears as if the CH bond activation rate increases as you go to smaller and smaller particles, just as we saw here. Okay, so I'd like to finish in the last 2 or 3 minutes and sort of leave you with what I don't know, what I don't understand very well, what makes this problem so complex. And that is, remember what I didn't explain to you, why the rate suddenly increases as I begin to deplete the oxygen. I'm going to do a very careful experiment. I'm going to take a gas-phase batch reactor where I know I have no exotherms, and I'm going to begin to let the oxygen be depleted, and I'm going to measure the rate constant for methane combustion on this system. And I'm going to get a beautiful horizontal line that effectively says that my rate is purely first order in methane, as I showed you earlier. And I'm going to push it too far. I'm going to get to this rate constant now as I go to very low oxygen pressures. And look at what happens. There's almost a phase transition. There is a sudden acceleration of the rate as you begin to generate holes on that oxygen-covered surface. There is an additional pathway that happens only rarely at very low oxygen pressures, and that is that you begin to go through a mechanism that appears to be much, much faster and has a much larger rate constant than what you have there. So now we have 3 ways of activating methane: on a clean surface, on an oxygen-covered surface, and on a pair that appears to be very, very reactive, which is the only type of mechanism that ends up leading to what appears to be partial oxidation. But it is not practical, because it only happens at the very end of the methane conversion when you have almost depleted all the oxygen. The rest of the time, all you're doing is combustion. Okay, the same experiment in a flow reactor and in a batch reactor, because I think is illustrative. Here's the methane rate, here's the methane rate. The O2 is getting consumed, the O2 is getting consumed. Look at what happens here as I deplete the oxygen, the rate goes up. Look at what happens here as I deplete the oxygen, the rate goes up. Look at what happens when I get over here, the rate begins to decrease. Look at what happens when you get over here. This right here and this right here is CO2 and steam reform. And look how small the slopes are. Those are the rates of reforming being, again, a factor of 10 lower than for combustion. You can follow this and you can convince yourself that effectively in this region is the only time that you make CO by a direct path. The rest of the time you're making CO2 or you're making it via a secondary route. The problem is that things get much more complicated as you now begin to do your usual routine, which is go from metal to metal. Platinum is different. It is not totally different, but it is very, very different. It follows the opposite trend with dispersion, and if that were enough, it has an additional nuisance. And the nuisance goes as follows. Remember how I said before that the rate increases as O2 is depleted. On platinum, the rate increases as O2 is consumed. In other words, you don't have to deplete it before you get to this negative order in oxygen that I showed you for rhodium and ruthenium. The rate is increasing even before. There's negative order kinetics all the way through the system, and then of course it comes down. The CO2 reforming rate out here is quite low. You're doing combustion on a side pair all the way at all oxygen concentrations on the surface, and you're actually making CO2. You're doing catalytic combustion. This is what we have found earlier, by the way, in palladium oxide, and this is the interesting region. So my last slide shows you the level of ignorance at this point about what is going on, but at least a feeling that we know where we're heading with this chemistry. This is on platinum, the CO2 reforming and the steam reform. Here's what it looks like for methane oxygen. It is actually not first order, but second order. This is what the O2 dependence looks like on platinum versus the zero order that we saw earlier. If we assume that there are 2 rates that matter, the rate at which you effectively take the oxygen away and the rate at which you replenish it, and you get a rate expression, this is the rate expression that you get. And those 2 trend lines that you see right there are effectively what you expect from that rate expression. So you're actually activating on an oxygen side pair all the way at those oxygen concentrations on platinum. Why? Because platinum has a lower binding energy for oxygen by all appearances than what you have on rhodium and ruthenium, and therefore it is easier to generate one of those vacancies. This, by the way, also accounts for the dispersion effects, but that's a bit of a speculation at this point. Okay, I have finished my talk, and I hope it has not been an overwhelming tour at this point. I have taken you through about 3 years of work where we began totally ignorant and naive, and we're remaining very close to effectively being able to be as naive as we were at the beginning. We have not had to introduce too much complexity along the way. Effectively, this seems to explain most of what we see quite well. We don't need more than one mechanism to account for even things like water gas ship, carbon formation, and now the methane oxidation reaction. As far as we can tell, what matters in this system is how coordinative unsaturated the metal atoms are on the surface, something that will increase as you make smaller and smaller particles. The identity and how many neighbors you have is the only thing that matters, and it matters because the CH bond activation rate cares, and that is the only thing that limits the overall rate of this reaction. And finally, it probably will take us a little bit while and a lot of help from theory, I hope, in trying to explain why these 3 different modes of activating a CH bond have so dramatically different rate constants. In other words, the 3 ways by which you can activate a CH bond are actually leading to very significant rate constants for that reaction. And we can measure that reaction from an experiment inside a tubular reactor, and we're looking at the chemistry in the absence of the transport artifacts. Finally, I want to acknowledge my co-workers who have done a tremendous job for the last 3 years. BP, as part of the methane conversion cooperative, who have supported this work for those 3 years. Miguel Avalos for the transmission electron microscopy, and Joseph Matthew, because they do support the Burwell Award, for which I thank them. Thank you all.
We'll have time for a couple of questions.
Enrique, your rate expression shows first order methane, and the other term is the number of active sites, which when the surface is clean, that doesn't depend on the support, doesn't depend on the oxidant, CO2 or water.
Right.
Under conditions in which you do have carbon deposition, that term will be a function of whether you have CO2 or water, or what your support is.
I don't think so. If you had any influence whatsoever, let's assume that you have to activate your core reactant in order to change the extent to which the surface is covered with carbon. If that were the case, you would get a positive order in the core reactant concentration. The other thing that we have done that is we have looked at the rate of a structure-insensitive reaction before and after we do the reforming reaction, and we get the same identical rates. So at the conditions that we have run, we have no carbon. If you had carbon,
Yeah,
on the
if you
surface,
have carbon, that's what I'm saying. When you have carbon,
right.
that would be a variable. That term is not constant.
Right. If you become limited by CO2 activation and the support is able to do that, then you would get those effects. But you have those 2 requirements. Okay?
We have time for one more question.
Sorwin here. When do you measure the metal dispersion, and do you check it before and after the reaction?
We measure it before. We cannot check it after, because if you notice in the fine print, we use about 0.5 milligram of catalyst, diluted about 500-fold, in order to be able to make sure that we don't have any gradients. What we can do is we can carry out a reaction that we know is a clean structure-insensitive reaction, and we use CO oxidation before and after the reaction, and we see no change. So we measure the dispersion before, and we check that it appears not to have changed by carrying out a reaction before and after we do the reforming. That's all we can do with 0.5 milligram of gas.
We want to thank Enrique for a most enlightening